This is the Applied Statistics in the Healthcare series, and this is the 5th session in the Multiple Linear Regression course. In this session, we're going to look at our second set of case studies, and these are in the area of health economics, cost, and time. We'll do a diagnostic cost model. We're going to use the seriously ill hospitalized patient study, which is the support study by Frank Carroll, and it is the study to understand prognoses, preferences, outcomes, and risks of treatment. From that same data set, we'll do a prognostic time model, and we'll look at seriously ill hospitalized patients' length of stay. Let's begin. Okay, for case study 2, again, this is covering health economics, cost, and time. We'll do diagnostic and prognostic models predicting cost and length of stay during hospital stays. Two of the toughest models for model outcomes for linear regression would probably be time and cost. These are two very highly skewed outcomes that, as we know, outliers can be an issue for linear regression, but in this case we have very extreme values that make it difficult sometimes to get good estimates. The reason is that those outliers tend to dominate that regression or trend line, but we do have ways of dealing with it, and we'll cover that in this session. But before we begin, let's compare diagnostic and prognostic models. On the left side, we have some characteristics about diagnostic models, and on the right side, we have characteristics about prognostic models. And in that top row, we see that for diagnostic models, they're often called explanatory or retrospective models. For this type of data, we tend to investigate a certain phenomena that we've already collected data for, and so we want to understand how that whole process works. While for prognostic models, they're often described as being predictive and prospective. So we tend to have some sort of predictive feature that we're trying to get optimal estimates from in our model. We're often in our study design looking forward into the future, so we may assign predictions and then determine later if those outcomes match those predictions. For diagnostic data, for diagnostic models, it looks back at existing data. Both predictor and outcome values are already known. Provides hypothesis tests and effect sizes in that analysis. And for prognostic models, they are applicable to future data, but it is often developed on existing data. Uses variables with values available at study entry to make predictions. In other words, for prognostic models, we're calculating predictions at the moment that patients may walk into the hospital or maybe assigned a treatment, but we're making these predictions right at the very beginning, and we have no information on what that outcome may look like. So that's the difference between diagnostic and prognostic models. Diagnostic models have all the data in them, while prognostic models, we're often assigning predictions at the moment that patients walk through the door. And for diagnostic models, because we already know what the outcomes are, and we're not trying to use these real-time predictions, we generally have more predictors, and we also have results that have higher R-square. For prognostic models, we tend to use fewer predictors to make those same-day predictions, and we generally have lower R-square values. And for diagnostic models in a study on cost, they'll include length of stay and death because all patients were discharged. And for prognostic models in a study on cost, we will not include length of stay and death because that is unknown at admission. And just to give you a review of the study, it's called the Study to Understand Prognoses and Preferences for Outcomes and Risks of Treatment. It's a support study by Professor Frank Harrell at Vanderbilt. This is the study to examine the outcomes of seriously ill hospitalized patients. Data was collected from 1991 through 1994. The sample size is 9,105. Two of the outcomes are cost and length of stay. Most variables are lab values from the patient's stay with some demographic information. Some variables have missing data as high as 50%. This leaves us with the question of how to build a reliable model with high missing data and highly skewed outcomes. Alternatives to the linear model include the Cox proportional hazards model. Here are the predictors. We have a long list. We have at the top age, death, sex, death in the hospital. And we can see in yellow we have our two outcomes that we're going to cover in this case study. We have the length of stay, days from study entry to discharge, and then we have the outcome of charges, and those are hospital charges. We also have things such as the diagnosis group, the diagnosis class, number of comorbidities, information about background characteristics about the patient. We have different risk scores. We also have predicted 6 months survival time based on the physician predictions. A list of different disease indicators, and towards the bottom we have a long list of lab values that we can routinely get. So we'll begin with our diagnostic model, and this is a model on cost. The topics that we're going to cover are missing data, single and multiple imputation, and model selection. So for the overview, we have a significant model with all predictors, but our 9,105 sample size shrunk down to 867 because of missing data. In other words, regression uses list-wise deletion, so in that long list of predictors, if there are any missing data in there, then those cases with any missing data, and that's either in the outcome and predictors, those get deleted from the analysis. So if we were to use all of those predictors in our analysis, that would reduce our sample size from 9,105 to 867. Because of that, we need to rethink the model and deal with missing data. This is the reduced model with the bigger sample size. And we see that charges equal sex plus age plus hospital death, and the remaining predictors. So we'll begin with looking at descriptives, and these are the means of the outcomes by quartiles or categories. For example, when we look at days from study entry to discharge, the length of stay, we see a strong linear trend. We see that for every quartile, and that's the mean for that quartile is indicated by that red dot. So for each of those four quartiles, we see that as the length of stay increases, so does the cost. And that's a strong linear trend. And then also with age, we see as patients get older, we actually see their costs go down. And we also have large group differences, such as a death in the hospital. That's about a 40,000 difference between those who had a death in the hospital and those that didn't. And then for the diagnosis or disease group, we see a lot of big group differences. And we can see the rest of the predictors and their distribution on charges. And then we can look at the second half. And again, we see, for example, on bilirubin day, we see a strong linear trend, although it's important to note that for a lot of this data, we have missing data. We have the sample size on the right, and we can see how much of that adds up to the 9,105. Just because there's so many predictors in here, the sample size is not listed for each category. Sometimes it skips, but we should keep in mind that we do have a lot of missing data in this data set. And in this slide, we're going to look at the model performance of different models. On the left side, we have the type of model, and then we have it broken up by the type of imputation there is. So on the very top 5 rows, we have no imputation. The middle 4 rows, we have multiple imputation. And the bottom 2 rows, we have what's called single imputation. And so in each column, we have information about the sample size that we find in that data set, the R-square, the validated R-square, the AIC, which is a way to another way to judge model performance. It's the Akaike information criterion. And then we have, on the very end, we have the mean absolute deviation, and that tells us what's the average deviation as an absolute value. And so in that very top model that's named a linear and additive, we see that there's about 2.5% missing data, and we see that also in the top 3 rows. So if we recall back to earlier sessions, we know that when we have 2.5% missing data, that's not a lot of missing data. So we can tend to ignore those values or impute them with the median or mean value. In our example here, we're just going to ignore the missing data since it's not a lot. So we see that those R-square range from about 0.497 to 0.561, and the validated values are not much different from that. And then we have, in that second row, the description is top-coded charges. And so that for that data, we've top-coded the charge values, and those are to about the top 5% are top-coded at that lowest value within the top 5%. And then in that third row, we have top-coded length of stay. So we've also top-coded the length of stay variable since it's also skewed. And in addition to that, we've also top-coded charges. Fourth row, it's top-coded charges, and it's nonlinear on all our predictors. And in that fifth row, we have imputations on the above model. So you can see under the sample size, it's 9,105. And for the next set of model performance values, we use multiple imputation. As you'll recall from earlier sessions, multiple imputation is the process of having various predictors predict the values of each predictor value that's missing. So if we have missing values in age, we're going to use sex, disease group, and all the other predictors to predict that missing age value. and then it rotates and continues, where other predictors are predicting the value of your missing predictor of interest. And then it's called multiple imputation because when we then do the regression, we're repeating this process multiple times, and we get the average coefficient from those multiple imputations. So if we've done multiple imputation 10 times, we get the average of those 10 coefficients, for example, with age. And so in that we have, under multiple imputation, we have all predictors. We have them imputed all predictors. And then we have all our predictors with splines. And then we have all predictors imputed with splines. So you can see that in the end column, it goes from 867 to 9,105. And then we can see how they compare with the imputed values. We can't get validated R-square because in that process we're using imputed values to impute our validated R-square. So we have to leave those blank, but we can get an idea of how well they perform based on the R-square, the AIC, and the MAD. And then for the single imputation section, we have all our predictors, and then we have all our predictors with splines, and we can see what the model performance values are. And in that, we actually are using the 9,105 cases in that data set. In this case, with how single imputation and multiple imputation differ, with single imputation we can get an imputed value for each of our missing values. Because we're not using multiple imputations where we're trying to get the average. With a single imputation, we can we can create a data set with all our missing values imputed in that data set. This should read 9,105 in this data set. But in this we can compare how each of the different models perform and what's the benefit from these different methods that we've used. And in summary, it's recommended to use a model with the top coded cost and no imputation. A diagnostic model is for explanations. A different model would be better for different purposes. Only 2.5% of the data is missing, and there's really no imputation required for those predictors. We used multiple and single imputation or no imputation at all. We allowed nonlinear model fits, no interactions used. We should consider principal components analysis. We have a lot of lab values that may be correlated in some way, so we can combine those predictors if it makes sense. Better performing models and smaller data sets fail to maintain their R-squared after model validation. And we see that in these different models where, for example, when we're looking at all predictors, all X with splines, that brings our data set down to 860 rows of data. We get I think actually the highest R-square at 0.681 because we're doing that. But our validated R-square takes a big drop and goes down to 0.572. So we do have better performing models and smaller data sets, but that's really just represents a very certain type of the population, and we fail to maintain that high R-square after model validation. Multiple imputation was a bigger help when there was a high level of missing data. In that fifth row in that top section, we see that reads as imputations on above model. When we went through the entire process of multiple imputation, that R-square only went up from about 0.597 to 0.598. So there was a very minimal impact through multiple imputation. But when we added in all those other predictors, then there was a big increase. And I think I forgot to mention in this top section, we don't always have all the predictors in there. We just kept the main ones that would give us 8,872 rows of data. So multiple imputation wasn't a big help when we had fewer predictors that had only 2.5% of the data missing, but when you added in all those other predictors, that did help performance. And the benefit of single imputation over multiple imputation is that it allows one to create a data set with the missing values replaced with actual values. Multiple imputation averages out effects over numerous imputed models. Therefore, we can't get one single data set for multiple imputation. And here's the model summary. We see that in this model summary graph, it shows effects when going from the 25th to the 75th percentiles in continuous predictors, or 0 to 1 in binary values, or the most common category compared to other categories in factors with many levels. And for this model, it's the linear and top-coded with no imputation model. We have a dashed vertical line at the value of 0 on our top axis. Values, predictors with confidence intervals to the left of that 0 indicate decreases in cost, and confidence intervals that are to the right of that 0 indicate increased costs. For example, longer lengths of stays tend to increase hospital costs, while older patients tend to have lower costs. And so we can see how, and we can interpret these results as the length of stay effect is very significant. The p-value is less than 0.001. If there's an expected increase in cost by $1,361 for each additional day in the hospital after controlling for other predictors, the difference is in expected cost for those at the first and third quartiles of length of stay, which is 6 and 20 days. That expected difference is $19,049. So that's a big drop. That's a big increase in cost, going from a low length of stay to a high length of stay for seriously ill patients. And at the bottom, the last rows in this graph, we see different confidence intervals between patients in the disease group sepsis compared to all other disease groups. Sepsis would be at that dashed line, and for example, when we compare COPD and slash acute renal failure slash multiple organ system failure with compared with it's COPD compared to ARF slash MOSF with sepsis. And you can see that that one's about $23,000. That stays about $23,000 less than it is for patients with sepsis. And another way we can interpret that result is the disease group effect is very significant. P-value is less than 0.001. There is an expected difference in cost between the sepsis reference group and the lung cancer group. And that expected difference is $33,461, with sepsis costing more after controlling for other predictors. So we can see a big difference in cost. This in this graph, and we can see that sepsis, like today, is going to be one of your highest costing diseases. And so in this, we're going to look at the variable importance. The most important predictors on Y have dots furthest to the right. And we see the bottom three, or the most important predictors on hospital costs would be a hospital death, the diagnosis group, and the length of stay. And we see the same thing today in our hospitals. Bigger costs are related to longer stays, sepsis, and death in the hospital. And here's the variable importance, and this is the full model. That means all the predictors that we examined, and we're using it from our imputation data. So we can see on the very top that these predictors have low predictive power. Consider excluding them if you want a more parsimonious model, if you want kind of a more efficient model that requires less effort to download all the data. And circled in green, these are important predictors that have a high level of missing data and could be rightly or wrongly left out of certain models. So everything from the albumin ALB_I to the bilirubin BILI_I, those come out of our imputed data, so they had a lot of missing data. They're important predictors. We shouldn't ignore them in future analyses, but in this data set they had a lot of missing data, so they weren't always in every model. But it's important to note that imputation can help us make use of data that is missing but still very important to knowing our outcome of hospital costs. And for these partial prediction plots, they show trend lines while holding other predictors constant at their average value. And so these show the trends while making all things equal. And we see that for the length of stay, we can see that's a very strong linear trend. Because it's such a strong trend, all of these other partial prediction plots, those trends look flat. If that wasn't such a very strong trend, if we were to remove SLOS, which is the study length of stay, if we were to remove that from the analysis, we would see much more steep looking trends, especially for age. It's got a strong decreasing trend, and the APS, which is a risk score, and that's got a strong increasing trend. So it's just that the perspective on the plots that these mostly look flat, but many of these are very significant predictors. It just points out how important knowing the length of stay is to predicting that total hospital cost. That's a really strong trend that we're seeing. So that means that as the length of stay gets longer, the hospital cost gets higher. And so now we're going to look at our prognostic model, and this is the length of stay. And in this, we're going to cover the topics of developing a parsimonious model through model approximation. In other words, use the fewest predictors that remains equivalent to the gold standard model. And the gold standard model is often our full model where we are using as many predictors as we find important. A prognostic model can be used to make predictions the moment a patient walks in the door. It uses the support data from the diagnostic model example and the single imputation data set that we created. And here we have the model summary. So we made three models. We had a linear model, and that again, we're using the data set from our single imputation, so we actually have that missing data filled in for all our predictors. From that model that's linear and additive, the R-square effect size is small. The R-square is 0.127. Our validated R-square is 0.117. The AIC and MAD values are to the right. And for a linear, when we use the linear model that has the top-coded value for length of stay, we get a medium effect size. The R-square is 0.202, and the validated R-square is 0.193. And for the third model, we have a model that's nonlinear and does use a top-coded length of stay. And for that, we get a large effect size. The R-square is 0.306, so that R-square is the large effect that we're talking about. And the validated R-square is 0.287. And when we look at the AIC and the MAD, for that, both values are better when they're lower. We see that they have the lowest AIC and the lowest MAD as well. And for this fourth row, that represents an approximated model. So for this, our goal is to make predictions on the fewest predictors, using the fewest predictors as possible, that still gives us a pretty high level of predictive power. And so, in other words, what we're going to do is we're going to trim the unimportant predictor variables. Not all predictor variables are equally helpful. Some have very little or almost no effect after you take into consideration all of the other predictors that are in that model. So for this approximated model, we again have a large R-square effect size. The R-square in the model is 0.289, and when we do model validation, that R-square only drops down to 0.279. So we have an AIC that is very close to the nonlinear and top-coded model, and in our example here, we're going to consider this the gold standard model. And our MAD value is the same as the gold standard model. And we see that each model is improved by using better methods. The approximated model with 15 predictors is as predictive as the gold standard model. The nonlinear and top-coded length of stay at 28 days with 26 predictors. So that 15 predictor model is as good as a 26 predictor model. And so we'll do a model summary. We're going to look at the 26 predictor model. And again, when we look at that value of 0 and the vertical dashed line below it, we see that when the confidence interval for each predictor is above that value of 0, above or to the right of that dashed line, those are predictors that represent increased cost when with higher values of those predictors. While on the left side, the predictors with confidence intervals, which are the blue bars and the red dots in the middle, when those predictor values are higher, that tends to decrease costs. And again, an important thing to point out is the large group differences when we're looking at the different diagnosis or disease groups. We see big differences between acute renal failure / multiple organ system failure with sepsis diagnoses compared to, for example, COPD, CHF, and other diseases as well. And now we're going to look at variable importance. And again, it's important to note that the values with their dots furthest to the right indicate the most important predictors, and these are also the predictors that are at the bottom of this graph. So the most important predictor in predicting length of stay would be the disease group or the diagnosis group, the APS risk score, and the 6-month survival prediction by physicians. And for this model, I allowed us to have nonlinear trends in our continuous variables. For this, we're mostly looking at creating predictions rather than explaining this model. So again, a prognostic model is there to assign predictions for different levels of risk, while a diagnostic model is to explain different things. What we saw was in our diagnostic model, length of stay was the most important predictor. So in determining cost, so what a common strategy might be in this kind of work is then once you've identified the most important predictor, you may want to develop a model to predict the chances of having a high or a low value for that key important predictor of cost. In this case, it's length of stay. So in this model, you can see all of the different linearity or nonlinearity in our trends between the predictors and the outcome. Let's see, you can see some go up, some go down. With APS, there may be your longer lengths of stay might be associated with higher or lower APS scores. And so here's an example of our modified model based on an equivalent AIC after deleting predictors. So we have a list of 11 predictors in this table, and we have that column that represents deleted. So if we were to delete the heart rate in that top row, that would leave us with the chi-square of 2.17. The p-value would be 0.7047, but it's probably most useful to go to that very last column on the right under r-square. And that 0.305 value indicates that if we were to delete heart rate from that analysis, that would leave us with an r-square of 0.305. We're making these decisions based on the change in the AIC. So what we want to do is find the least impactful predictors and see what our model r-square or our model reliability would look like after removing that predictor. So by removing heart rate, our r-square only drops from 0.306 to 0.305. So it's not a lot of change in that r-square. And if it takes a lot to get that heart rate, maybe that's extra time that nurses use in their assessments, then we can save time and money that way. So if we were to then look at after deleting all 11 predictors, we see that in that 11th predictor is sex. So that's one that, that's I think most easily found in our data. So it's just for purposes of going along with the analysis and the results that we're seeing, I've removed it. This is already generated for me, so at this point I haven't actually removed anything yet. But it does show what would happen if we did delete it. So if we were to delete all these 11 predictors, including this bottom one that says sex, the r-square would only go down from 0.306 to 0.301. So you can get rid of 11, almost half of your predictors. That's data you don't have to collect, data that doesn't need to be scored, data that we won't have any missing data issues with in the future, and your R-score only drops by 0.005. Removing the lowest predictive power variables will only change R-square from 0.306 to 0.301. And so that suggests that we can improve our model efficiency by removing variables. And another way to look at that would be something called model approximation. We can create a parsimonious model with an equivalent level of prediction as the full model or the gold standard model. And so what this does, it lists all of the predictors and the level of R approximated R-square that we have after removing those predictors. So we can see that the numbers on the top right, which is very difficult to see, you can't really see it, but it begins at 1, meaning that first predictor that we remove, or the least predictive variable. If we remove it, it'll leave us with close to 100% of our predictive power. And so you read it from top right to the bottom left. So what we can do is we can remove the bottom 15 predictors and still have at least 95% of the predictive power. And so in this, on the x-axis, we see that 0.95 highlighted, and that represents the proportion of full model R-square remaining after deletion of each predictor, and we should select a stopping rule that makes approximation inadequate. So if we go below that 0.95 mark, that's probably not a good idea if we want to get a model that's equivalently powerful as our gold standard model. But a general cutoff stop would be 0.95. So we can drop the predictors to the right of that 0.95, which is about 15, and we could end up with an approximated model that has about 95% of the predictive power of our gold standard model. And so in these results, we can see the actual predictor names and the actual remaining R-square. For this model approximation, removal of the 11 lowest predictive variables retains 98.3% of the gold standard model's predictive power. So we can see if we were to remove diabetes at the top in row 1, that would give us 90.9999788 of our original R-square. So if we were to remove 11 of these predictors, that would take us to row 11. That will leave us with 0.9831661 of the R-square from our gold standard model. So this is a great way to reduce the model size. Remember, in this data we have a lot of missing data. So in this data set, I'm looking at imputed results. When we're actually doing a model, if we put one into production, we won't have the ability to impute and find missing data for all those patient values that as they walk in the door. So this is kind of using this imputed data is kind of a best case scenario. So we really, knowing how much missing data we have, we should really take advantage of ways to reduce the potential issues we would have by introducing all predictors into our model. And in this slide we have the nomogram, and again, that's something that we can share with our clients or any clinical staff or our own coworkers to show them how you can get model predictions. So in this, you just look at your predictor. Say if we have a 90-year-old patient, we would look up to that very top bar. That's about 24 points or 25 points. And then we would do the same for each of these different values. Let's see. If we go down to the disease group, if we go to the right, We see it's acute renal failure / multiple organ system failure with sepsis. And if we look at from that mark, takes us to about 48 points. So if we sum up all of these values for each of the different predictors, we get a total points, and say our total points comes out to be about 300. We would look under that 300 and we would see that predicted length of stay would be about 12 to 13 days. So this is just a great way to show what predictions might look like. We have nonlinearity in there, so that becomes a little bit more difficult to describe, because going from the age of 70 to 80 won't have the same added number of days as going from 80 to 90. So a 10-point change depends on which 10 years are we looking at. But this is just a good way to show that without having to do math calculations to try to figure that out. It's all right here on this nomogram. And in summary, for a prognostic model that provides only predictions, the approximated model would be the best choice. It has a predictive power close to the gold standard model while using only about half the predictors. Many predictors have high missing values, so this would save the effort of collecting all of the data. Our large R-squared effect size isn't nearly high enough to be accurately used to predict a patient's length of stay, but it can identify higher than expected lengths of stay. We can better predict for important groups like disease groups to help with the decision-making, scheduling, and allocating of resources, etc. So, although we can make predictions for patients, but those won't be. We wouldn't expect them to be accurate. They can help inform staff to say this patient has an above average expected length of stay, or this patient has a very quick length of stay that we predict. So we can kind of rank patients in terms of who has a greater risk or who has a longer expected length of stay. But if we wanted to give actual predicted values, we would actually do better with groups such as our disease group. And because that's the most important predictor, and that would be an ideal situation that we can start to assign expected lengths of stay for patients in these disease groups. On the average, for those patients in the disease groups, we'd probably come very close. We may not be, if we had 3 patients in the same disease group, we may not be nearly as accurate in predicting each patient's expected length of stay, but on the average for all patients within each disease group, we'd probably do a pretty good job in predicting those expected lengths of stay. So here's an example of our different disease groups. And for example, the sepsis group, they tend to have 16-day lengths of stay. Well, if we were to compare them to the patients with lung cancer, their lengths of stay are closer to about 9 days. And so this is where we'll start next week. For our final case study, I will go ahead and show you how I got those, how I got the results that indicated which predictors we wouldn't need in our model prediction. So in the Model Builder tab, we have the model that we were looking at for the top-coded length of stay. And that's top-coded at 28 days. And we have our model results here. But let's go up to the Modify tab. And at the top, we can see We can see which predictors based off of the AIC value on the column second to the right. We can see that it shows which variables we can remove from our model and not make a significant change in our predictive power. At the very bottom, it gives you the factors in our final model, and it gives you the expected coefficients after deletion of those predictors. And we have something similar in the Approximate tab. This is a part that has the model approximation, and this is a graph we looked at earlier. It gives you an idea of which predictors you can drop. Our cutoff is 0.95, and that would be the second vertical line to the right. It's between 0.9 and 1.0 on the x-axis. So this is a visual to show you about, this gives us the idea that we can drop many predictors from our model and still retain a high level of model approximation in terms of our R-square. We get something close to our gold standard model. And then below that, it has it lists each predictor with the remaining R-square next to it. And we went down to the 11th. We dropped 11 predictors, and it left us with about 0.983 of our R-square compared to the full model. And then we have the summary of the approximate model. And this is all found on the GUI that I have. And we'll continue more next week.